All right, so now we're going to discuss the mathematical laws that govern the properties of gases. The first of these laws is known as Boyle's law. Boyle's law states very simply that as pressure increases on a volume of gas at constant temperature and constant number of moles of gas, the volume decreases. So you can imagine that if you have a gas at a certain volume and the pressure increases on that gas, the gas gets squeezed so it occupies a smaller volume. The converse is also true. As the pressure is released, as the pressure decreases on that volume of gas, it will expand. Okay, so basically what this law is saying is that pressure and volume are inversely related for gases. As pressure increases, volume decreases. And to describe that inverse relationship mathematically, we can just use the equation P1V1 equals P2V2. So this is the mathematical expression for Boyle's law. So it's very simple to do some quick Boyle's law problems. For example, let's say that a gas occupies a 0.3 liter volume at 1 atmosphere. What would its volume be at 2 atmospheres? So I am going to arbitrarily say that this 0.3 liters is going to be V1 and the 1 atmosphere is going to be P1. The P2 is going to be the other pressure, so let's call that 2 atmospheres P2. And I can rearrange Boyle's law to solve for V2. So V2 equals P1 V1 over P2. Plugging everything in gives me 0.3 liters at 1 atmosphere divided by 2 atmospheres. So the atmospheres cancel, and I'm left with 0.150 liters. So the volume of the gas at 2 atmospheres is 0.150 liters. So you can see what happened in this problem. We started at 1 atmosphere and we doubled the pressure to 2 atmospheres. And as we did so, we cut the volume in half. Okay, so as the pressure doubled, the volume was cut in half from 0.3 liters to 1.5 liters. Okay, so this makes sense because as pressure increases, the volume that the gas occupies is going to decrease. Okay, we can talk about a similar mathematical law for temperature, relating temperature and pressure, temperature and volume rather. So this is Charles's law, which states that as the absolute temperature increases, assuming constant pressure and number of moles of the gas, the volume that it occupies will increase. So this is a direct relationship. As the temperature increases, the volume increases too. So the mathematical equation to express a direct relationship like that is going to be V1 over T1 equals V2 over T2. So this is the mathematical expression of Charles's law. Now, Charles's law refers to absolute temperature. So whenever we're plugging in temperatures here, you must use the absolute scale, which is in Kelvin. So you must use kelvins for the temperature in Charles' law. And just as a review, if you take the Celsius temperature and add 273, you get the Kelvin temperature. So you can always interconvert between Celsius and Kelvin. This law means that in theory, at 0 Kelvin is absolute zero, you would have an undefined expression here. Your gas would have no volume, okay? This is one reason why 0 Kelvin is called absolute zero. You can't have a temperature below 0 Kelvin because then a gas would have negative volume, which is impossible. It is not possible for a gas to have negative volume. So this is why absolute zero is 0 Kelvin. Absolute zero is a temperature that has never been reached in the lab, although nano Kelvin temperatures have been achieved in the lab. Okay, So whenever you are plugging in temperatures, they're going to be positive. Okay, that's another reason you have to use Kelvin, right? Kelvin temperatures can't be negative because 0 Kelvin is absolute zero. And a gas cannot occupy a negative volume. So you have to use Kelvin temperatures in this equation. Let's do an example. A 0.3 liter volume of gas is heated from 27 degrees Celsius to 227 degrees Celsius at constant pressure. What then is the new volume going to be? Okay, so let's assign some variables and then plug these into Charles' law. I'm just going to arbitrarily say that V1 is 0.3 liters, and that has to go with the T1 of 27 degrees Celsius. Now, I need to add 273 to get the Kelvin temperature, so this is going to be 300 Kelvin. Now, what else do I know? I know T2. T2 is 227 degrees Celsius. So once again, I need to add 273 to get the Kelvin temperature, 500 Kelvin. So we are looking for the volume at that temperature. So V2 is going to be what? Here we have Charles's law, V1 over T1 equals V2 over T2. V1 over T1 equals V2 over T2. So if I rearrange this equation to solve for V2, V2 equals V1 times T2, multiplying T2 by both sides by T2 rather, over T1. And that's going to be 0.300 liters times 500 Kelvin divided by 300 Kelvin. So the Kelvins will cancel, and I'm going to be left with the volume in liters. And that volume is going to be 0.500 liters, it looks like. So we can see that as the temperature went up, the volume went up as well. This is a direct relationship. This should make sense. As temperature increases, the gas is getting hotter, the particles are moving faster, and they need more space to move around. So as temperature increases, volume is going to increase. That is Charles's law. All right, now you can combine these pressure, volume, and temperature relationships in Boyle's and Charles's laws into one big law, which I'm going to call the combined gas law. The combined gas law just combines Boyle's law, the P1V1 law, with Charles's law, which is V1 over T1. So P1V1 over T1 equals P2V2 over T2. This is just a combination of Boyle's and Charles's laws, which I'm calling the combined gas law. We can do problems related to the combined gas law. For example, a gas sample occupies a 0.5 liter volume at 25 degrees Celsius in 1 atmosphere. What will be its volume at 200 degrees Celsius and 4 atmospheres? Okay, so let's assign all our variables here. Let's figure out what we know. I'm going to just take this first stuff and call this volume V1 and this temperature T1 and this pressure P1. And the 200 degrees Celsius will therefore be T2, and the 4 atmospheres will be P2. So I need to figure out what V2 is. V2 is my question mark here. Remember, you have to convert the temperatures to Kelvin. So T1 is 25 degrees Celsius plus 273. That's going to be 298 Kelvin. That is room temperature. T2 is 200 degrees Celsius. And once again, I have to convert that to Kelvin. So that's going to be 473 Kelvin. And the pressures I can just leave in atmospheres. So let's think about what's happening in this problem. The temperature is increasing, right? From 298 Kelvin to 473 Kelvin. So as the temperature increases, what do we expect to happen to the volume? Well, that's a direct relationship, right? Charles's law. As temperature increases, we would expect the volume to increase as well. But what's happening to the pressure? Pressure is going from 1 atmospheres to 4 atmospheres. So what would we expect to happen to the volume there? Well, pressure is definitely increasing. And as the pressure increases, what do I expect to happen to the volume? Well, as the pressure increases, I would expect the volume to decrease, right? As pressure is increasing, that gas is going to be squeezed to occupy a smaller volume. So look what's happening here. I have two opposing forces here. So I have to do the math to figure out which one is going to kind of dominate. And this is where the combined gas law comes in handy. P1 V1 over T1 equals P2 V2 over T2. I want to rearrange this to solve for the unknown, which in this case is V2. So reorganizing this, V2 is going to be equal to P1 V1 times T2 over T1 times P2. Okay, so plugging in all of my variables, I'm going to plug in 1 atmosphere for P1. V1 is going to be 0.500 liters, I believe. Let's check that. Yep, V1 is 0.5 liters. And T2 in Kelvin is 473 Kelvin. T1 is 298 Kelvin, and P2 is the 4 atmospheres. So let's cancel the units to cancel. The atmospheres cancel and the Kelvin cancel. So I'm left with liters. And V2, once I do the arithmetic, comes out to be 0.2 liters. So we can see that the volume is actually going down. So that means that the pressure is going to be the dominant force here. Basically, pressure wins, but it's not winning as much as it would have if there hadn't been the temperature change. So there you go. That is the combined gas law.